Okay, this is the fourth video in the sequence of videos for Chapter 23 on geometric optics. This video is on total internal reflection. Let's go ahead and begin. If light passes into a medium with a smaller index of refraction, the angle of refraction is larger than the angle of incidence. That's shown in this diagram here. Looks like we have some source of light incident in water, and it looks like it's going into air. We can certainly see the light ray bends away from the normal. Now, as we continue to increase the angle of incidence, we find a critical angle, an angle that creates an angle of refraction of 90 degrees. So let's go ahead and define that. There is an angle of incidence for which the angle of refraction is 90. We call this the critical angle, theta c. Let's see if we can figure out a way of calculating that angle. We, of course, are going to use Snell's law for this. So Ni sine theta I is equal to Nr sine theta r. Now this is a special angle, so let's go ahead and replace theta I with theta critical. Is equal to Nr, the sine of, well, theta r. The critical angle is defined such that the refracted angle is 90 degrees. So let's go ahead and put that in here. Of course, we know that the sine of 90 degrees is 1. So if I want to find theta critical, let's first find the sine of that. So I could find theta critical as just the inverse sine of the ratio of those two indices, so Nr over Ni. Now that information is hidden here, if you will, but that's how we develop the angle, or determine the equation for the angle for the critical angle there. If the angle of incidence is larger than this, then no transmission occurs. This is what we call total internal reflection. So what's really important here is when we have an angle that is bigger than theta critical, such as shown here in case L, we don't get any refraction at all. As a matter of fact, what we get is complete reflection. So the entire light beam is now reflected back into that water medium. So this picture over here sort of shows that as well. Here I have some sort of light beam, looks like it's fairly wide, striking a mirror that has like 3 different reflective surfaces, each one sort of reflecting the light at a different angle. Well, you can see these two are exiting the water, refracting away from the normal, but this particular one is at an angle that is greater than theta critical. And what that means is all of the light is actually reflected back into the water. None of it escapes. Now, effectively, the interface itself is serving as a mirror. What's important here is that it is a truly perfect mirror. There is no loss of light out of that medium. Even the best mirror cannot do that. So the best mirror will absorb some of the light. In this particular case, we get all of the light transmitted back into the incident medium. Now, there's all sorts of applications that rely on total internal reflection. Binoculars often use total internal reflection. This gives true 100% reflection, which even the best mirror cannot do. So I talked about that on the previous slide. If I have my eyes over here looking at some distant object, we're going to get the clearest image using total internal reflection that these prisms will do. And again, you can see how these things are sort of angled here to make sure that the incident beam of light is at an angle greater than the critical angle. So all of the light will be reflected through this set of binoculars. Now, the fire in diamonds is based on total internal reflection and dispersion. These diamonds are cut in a special way such that it captures all of the white light that might be coming from the room that we're in or maybe outside. All of that light that strikes the top of this diamond is totally internally reflected by being careful to cut these angles in a certain way so that all the light sort of stays within the diamond. And of course, all of it's going to then exit out the top. Now, we would give it that would give it a very bright sort of reflected light coming out, sort of give us some nice sparkle. Interestingly, over here on the edges, you can see that these are cut in an angle such that the angle of incidence is really close to the critical angle here, and we're going to get that light to come back out here, but it's going to be so tightly bent, really close to an angle of refraction of 90 degrees, that we're going to start to separate out the white light into its constituent colors. So we start to see some separation, which we call dispersion, and we get sort of that fire in the diamonds. Now, the real interesting and important application for total internal reflection is it is the principle behind fiber optics. So today's information-based society really relies on fiber optics to transmit information great distances and also at very high speeds. So we would not see all of the communication boom that we are currently seeing. We would not see that without the invention of fiber optics. Light will be transmitted along the fiber even if it is curved. And an image can be formed using multiple small fibers. That's what this picture is showing here. But really, the super important application of total internal reflection is how we can sort of use fiber optics to sort of act as a almost like a hose for light. So we can send information along that fiber optic cable as a light beam, and we can do it very efficiently. Let me do a quick little comparison between copper and fiber optics. So most of the information that was communicated to us back in the 70s and 80s and maybe even into the 90s was done so through copper wiring. And so this little table sort of shows the difference between fiber optics and copper. The installed cost is quite a bit less for fiber optics, so it makes things cheaper to install. The life cycle is quite a bit greater, almost a factor of 10 greater than copper. The distance that we can send information along fiber optic cables without sort of re-amplifying the signal is quite a bit greater than copper. The weight is less energy or power consumed. And here's what we call bandwidth. We can transmit quite a bit more information per second with fiber optics than we can through copper. So if we want to download or stream maybe a high definition video, this will take us a lot less time. We get much better quality when we go through fiber optics. Plus, fiber optics are sort of immune to interference, and it's much harder to sort of break into it or to tap into that signal. So quite a few advantages. Let's go ahead and take a look at how we might apply total internal reflection to a few examples. So here we have 3 examples that I want to go through with you. Find the critical angle for water-air boundary if the index of refraction of water is 1.333. That's pretty easy to do. Let's go ahead and do that here. We have a little water interface with air. Again, N, you probably are starting to memorize these. The incident angle, or the index of refraction for water, rather, is 1.33, and for air, 1.0003. So we have a beam of light that's incident in water, strikes that interface at what we call the critical angle, and we just want to go ahead and determine what this angle is, such that the refracted angle is 90 degrees. Okay, so I'm going to do this right from the beginning like we did before, just to illustrate again that this is just coming from Snell's law of refraction. So Ni is equal to Nr sine theta r, and again we're going to let this be theta critical, and we're going to let this be 90 degrees. Okay, so the sine of theta critical would be equal to Nr over Ni. And so theta critical would just be the inverse sine of the refracted index is 1.0003. The incident index is 1.33. So we can calculate that. And I'm getting about 48.8 degrees. So the critical angle for water-air interface. Let's go ahead and do the number 1 here. Glycerin is used to make soap and other personal care products. Find the critical angle for light traveling from glycerin into air. So let's go ahead and draw that one here really quick. So here I have a glycerin. Looks like I missed a letter there, but you get the idea. Glycerin air interface. And so we have a beam of light that's striking that as well. I'm not going to go ahead and do all the math that I did up here, but let's go ahead and draw that. If I want to get theta critical, again, it's going to be the inverse sine of Nr over Ni. Well, Nr is still 1.0003. Ni in this case is a greater index, 1.473. And we get for that angle about 42.8 degrees. Let's pause for a moment and take a look at this. The critical angle being smaller, as it is here, means that we can actually have the beam of light strike the interface at a steeper or more perpendicular angle. It's going to be refracted a greater degree because of the bigger change from glycerin to air than we have from water to air. So we can tolerate a steeper angle here, or an angle that's more perpendicular, if you will, and still have it be reflected back into the surface. So it has to do with something called optical density. The greater the optical density, the slower the light will sort of travel through that particular medium. So we can actually have this thing strike that interface at sort of a more perpendicular angle and still have it be reflected back in. Our last example here, calculate the critical angle for light traveling from glycerin into water. Now I'm going to use this example to sort of show you the construction of fiber optics. So here we have a fiber optic cable, sort of pick that off the internet. Let's take a look at the construction here for a second. We have some fiber optic core. This is where we're going to send the light beam through. Notice that it is surrounded by some sort of cladding here. Now what's really important is that we have to have two different indices of refraction, and the index of refraction for the cladding must be smaller than the index of refraction for the fiber optic cable. What that means is that light will travel more quickly through this than it does through this. And as long as we can keep that angle of light striking that interface at an angle greater than the critical angle, this cladding is effectively serving as a perfect mirror, sort of keeping the light bound within the fiber optic core. Now we can take this thing and bend it any way that we want. As long as we don't exceed the critical angle, we should be fine to be able to bend this thing, snake it through maybe a building that we're trying to install the fiber optic cabling, maybe put it underground. We can have it really effectively act as a hose for light. So it's pretty cool technology. Now imagine that we were making fiber optic cable out of glycerin and water. Probably not two substances that we would use here, but let's say that I had some sort of glycerin cable. Let's see if I can't draw that so it looks pretty good. There we go. And for this particular example, we have maybe that glycerin is surrounded by water. So we have some sort of water medium on the outside of this. Okay, so water on both sides here. Okay, so since I have glycerin on the inside and water on the outside, this is going to act like a perfect mirror as long as we can keep the angle of incidence sort of above the critical angle. So it strikes here, strikes here, strikes here, and so forth. And we can use the total internal reflection to sort of snake that light all the way through this. No matter what those curves are, as long as we don't have too sharp of a curve, we should be able to keep that light in that glycerin. Let's go ahead and determine what that theta, that critical angle is. Again, it's the inverse sine of nr over ni. In this case, the refracted medium is water, and the incident medium is glycerin. So 1.473. If you perhaps make a mistake here, maybe you have these two numbers transposed, so you have 1.473 in the numerator, you would get a number bigger than 1. You take the inverse sine of that, your calculator is going to give you an error. We only get total internal reflection when we go from a slow to a fast medium, not the other way around. So sort of check your math as you're going through and doing that. And if you get an error, you might have put these numbers in incorrectly. Let's go ahead and calculate that. I'm getting about 64.5 degrees. So the critical angle between glycerin and water. So there we go, a few examples on total internal reflection.